Alright, so in this video I'm going to compare some simulations for different sort of algorithms for updating the parameters in a neural network. So we've got gradient descent, just standard gradient descent, and that looks like this, where x is x minus the learning rate times the derivative. And this is only for the 2D situation, by the way. And then we have the momentum, so gradient descent with momentum, where we have this parameter here, Vx, or this term here that's calculated with beta times Vx plus 1 minus beta times the gradient. And then you just update it like this. And then we have RMSprop, which is a little more complicated, but it looks like this if you're interested. I did do a video on gradient descent and gradient descent with momentum. Actually, I did two videos, one with 2 dimensions and one with 3 dimensions. So if you're interested, watch those first. It might give you a better overview of this topic. I haven't done a video yet on RMS, but this one is more so just going to be comparing how they look like on certain functions. I'm not going to dive too deep into the theory behind them or why you'd use them in. Well, I'll show some situations where you'd use one over the other. But anyways, let's get started. Let's look at this. So we'll just run it. This is the first function here. Alright, so we start there where the point is. Let's see what happens. So you can see that gradient descent and RMSprop both perform fairly similarly, but RMSprop does better. And gradient descent with momentum, it's not too far off. It does have that momentum tendency, so it goes up like this and then it'll go back down and kind of settle here at this point 0, which is the minimum, which is the solution to this. So in this one, RMSprop performed better. Let's look at another one. So this next one is a little more complicated, you'll see it. Just bear with me here. All right. So this is the function, the second function, and we're starting up here. All right. So this is an interesting one. Now, gradient descent and RMSprop, they both settle at this point here because the gradient is 0, and RMSprop doesn't have this tendency that gradient descent with momentum does, which will be able to, does it get over? Yeah, it gets over. So yeah, you can see that gradient descent with momentum manages to get over this bump here. And that way it can actually reach a more ideal minimum, which is down here. And I'm sure it would be able to actually reach down here to 7.5. It's a little bit laggy, but yeah, you see that gradient descent with momentum does a lot better in this instance. And that's because this local minimum up here, that's where the gradient is 0. So that gradient descent and RMSprop are kind of contained there. You can see that RMSprop manages to get over here a little bit, but it's not quite enough. Now you could play around with the learning rate, and if you had a higher learning rate, gradient descent would actually jump this entire bit here, and we'll just get here, for example, maybe on the next iteration, and then it would be allowed to get down to this minimum. But I think it's more smooth the way that gradient descent with momentum does it. I don't mean smooth in the mathematical sense. I mean smooth as in it just looks a lot nicer and it looks a lot cleaner as well. So yeah, it will settle down to this point 7.5. All right, let's look at another one. And I'm gonna make this one a little bit faster because it would take too long if I keep the pause higher. All right, I think that is good for that one. Okay, so this one we're starting up here in all these cases. And yeah, you can see that RMSprop goes very quick at the start. Now it slows down here, which is because it's hard to tell in this situation because it's quite zoomed out. But if you look closely, you can see that the gradient is very close to 0 at these bumps here. these bumps here, the gradient is very close to 0, so that's why our RMSprop will slow down, and momentum will slow down, and gradient descent will both slow down as well. So yeah, in this situation, you can see that RMSprop definitely won in terms of reaching a minimum fastest. Okay, what is the next example? And we'll go back to 80, and this time we'll pause for, I don't know, 0.1. If you're interested in like the coding aspect of it, then I go into the coding more in the previous videos that I mentioned. All right. Okay, we're starting up here at, looks like x in it equals 4. And yeah, look at this one. So RMSprop shoots off, and it kind of reaches the minimum there. But because of the way that it's constructed, because of the equations that are used, it looks like it just goes back and forth around the minimum. So it doesn't actually reach the minimum. So it looks like in this situation, gradient descent performed the best, and it manages to actually reach the minimum, which is something that RMSprop couldn't do in this function. Now, gradient descent with momentum, that reaches the minimum eventually, but it has this tendency to go up like this. And in this situation, the momentum is actually counterintuitive because it's not needed. Or there's no bumps to kind of go over with the momentum, but you'll see another example of that in a second. All right, so this is the last example. Okay, this one I'm going to show you what changing the learning rate does. So we're going to start with a learning rate of 0.1 in all these situations. Now, it will have a different effect compared to gradient descent and then gradient descent with momentum and RMSprop, because with gradient descent, it's multiplying the gradient here, just the gradient, but with momentum, for example, it's multiplying also Vx. So it's multiplying the entire Vx, which is multiplying the previous Vx and the gradient. And for RMSprop, it's multiplying all this stuff here, the gradient divided by the square root of Sx, and then Sx is this one here. All right, let's run this. Okay. So we're starting up here, I believe, yeah. Okay, so with this example, RMSprop converges very quickly to this minimum here, but that is not the ideal minimum. And you can see that with momentum, it actually doesn't quite reach this peak here to be able to get to this global minimum down here. So in this situation, the momentum wasn't enough. And you can see that it goes back down to this less ideal minimum. Now, what we can do in this situation is increase the learning rate. And just to be fair, I'll increase the learning rate for all the algorithms. And that's what I've done here. Don't worry too much about the actual code here, but this section here is for gradient descent. This section here is for gradient descent with momentum. And this section here is for RMSprop. So I'm just changing the learning rate for all the situations in this one. We'll run it again. Okay, let's see what happens this time. Okay, so RMSprop actually almost got over there. So it went here, and it looked like it went here or something, but now it's kind of settling down into this minimum. Gradient descent just goes down here. But then momentum now the learning rate is enough to actually get it over this bump here. And remember, if we look here, the learning rate is multiplying Vx, so it includes that momentum section. So by increasing the learning rate, we increase how much the momentum actually matters. So we can go back to there we go. So yeah, the momentum actually carried it forward here and allowed it to reach the global minimum in this case, in this little component of the graph. But essentially it reached the more ideal solution. And now we're going to look at what happens if we increase the learning rate even further. that. So in this situation, it actually allowed RMSprop to get over this bump here. And it does converge essentially to this minimum here. It kind of bounces around a little bit. I'm not too sure why it actually does that. I'm sure it's something to do with the way that the equation is constructed. But I haven't dived too deep into that yet, but it does converge at some point. So I guess you could stop the algorithm when it gets close enough to the minimum. And I wasn't gonna include this in the video, but I'll just show you briefly how I've kind of done this. You can specify an error and then the true solution. I've just set it to -1000, so it doesn't really change the code. But in this situation, the solution is what do I see, like 4.1? Let's just pretend it's 4.1. I could write -4.1 here, or 4.1 was it? And then the error, which is how close you'd be happy to reach the solution. So how close to the solution, I should say, that you'd be happy to be. And then what you would do is you just calculate the norm, which in this case, because it's just two-dimensional, is just the absolute value of x, which is the solution at a specific iteration of the algorithm, minus the true solution, which is, I've just called x sol, and that would be just solution here. And if that is less than or equal to error, you'd stop the algorithm. And that's similar to what I've done here. I won't go too deep into it, but that's pretty much what I've done here, where I'll only keep doing the algorithm if the solution isn't close enough. So once it gets close enough to the true solution, then I could just stop the algorithm. And that's essentially what you could do when you're running these algorithms in machine learning. If you have a good idea of what the loss landscape, I guess you could call it, what the loss landscape looks like, then you could kind of say, okay, when the algorithm reaches this loss, I'm happy with it, I'll stop it. And then I could maybe train it with a lower learning rate, so that kind of goes a little bit better, essentially, a little bit closer to the true minimum at that point. But yeah, anyways, you can see that in this situation, RMSprop was fine because the learning rate was heightened. But anyways, that is the video. Thanks for watching.